These are the problems that I gave at the end of class, and I asked you to rank these based off of acidic strength. So I want you to rank them from the most acidic to the least acidic. So when you take a look at these problems here, I highly encourage you to pause the video and answer that question. Rank these 1, 2, 3, 4, 5 acids in most acidic to least acidic. Then after you've come up with your answer, unpause the video and see the answer. So what are we supposed to do when we're asked a question about strength of acids? Well, we want to figure that out by looking at the conjugate base. So we've got to convert all of these to their conjugate bases. And so I'm going to do that right now. So you notice here, when we take an acid and look at its conjugate base, all we're doing is, there's 2 protons here, we get rid of it. I highlighted this proton to give you the hint that, hey, I'm looking at that proton, that's the acidic one. And we just get rid of it, and it's going to be the anion. Now, this proton, boom, gone, there, gone. That one's gone. Okay, so there's our conjugate acids. Sorry, our conjugate bases. So these are our acids, and these are our conjugate bases. And now we ask the question, the stability of these conjugate bases. And I like to use the cardinal rule to help us figure that out. So C in the cardinal rule stands for charge. And I look at all the conjugate bases here, and I see that this one's neutral, and every other one is charged. And we have learned that when you have a neutral species, if this is energy, a neutral species is typically lower in energy than a charged species. And that could be a plus charge or a negative charge. Positive or negative, charged species are just typically higher in energy. So what we found by using the cardinal rule is that this has no charge. So that's going to be, if we draw an energy diagram here and label these, let's label that A, B, C, D, and E. A is going to be the lowest in energy compound amongst these 5 because it has no charge. But then all these others do have charge. So we've already, from the first letter, we have 5 to choose from to figure out what's the most stable base. And the C tells us this has no charge, so that's the most stable. So that one's done. And we're done with the C because we've already looked at the charges. Now all these have charges. So how do we distinguish the relative stabilities of these guys with A? A stands for atom. And we can see here that the negative charge here is on a carbon, an oxygen, oxygen, carbon. So oxygen atoms and carbon atoms are in the same period, period 2. So which one's more electronegative? Oxygen. So the oxygens are going to be the most stable. And so it's between these two, C and D. So B and E have the charge on carbon. So we're just going to ignore that for right now and put those on the back burner. So now we just want to focus our attention on C and D. Now how can we figure out between those two what is the most stable conjugate base? That we just go to the next thing in our cardinal rule, R and D, for resonance. Do they have resonance structures? Yes, they do. They can have resonance structures. Both of them do. Okay, so that doesn't help us out because they both have resonance structures, okay? So what about induction there? Okay. What does induction mean? Let's look at a simple example just to make sure we understand that. Draw it right here for the moment. If we have a negatively charged species like that versus like this, induction is telling us that because this is a very electronegative atom, it's going to pull electron density towards itself through the sigma bonds. And when that happens, this negative charge is getting pulled towards the fluorine. And that is a stabilizing effect. So this one right here with the fluorine is more stable than that one because this one has no induction and this does have induction because of that electronegative atom. So if we go through that thought process, these two molecules right here already have resonance, so let's do induction. Do you see now that the molecule C has another electronegative atom, oxygen, and this one doesn't? So not only do both of these have resonance, but this one, or C, has induction because of this electronegative atom there. And so what it's doing is let's use a different color here. It's pulling electron density towards that oxygen. And so that has an inductive effect on that negative charge. So what we can say when comparing these two, this one D has no induction, but it has resonance. C has resonance and induction, so that's going to make that more stable than D. Okay, so we've got this one checked, that one checked off, that one checked off. Now it's just between B and E. All right. We see, if we kind of go through the same thing again, cardinal rule. C for charge, they both have a charge. A for atom, carbon, carbon. R and D for resonance, resonance, resonance. All right. Now look at this though, this thought process here. The more resonance structures that you have that can delocalize this negative charge, the more stable your molecule is going to be. So if I draw a resonance structure for this guy, we could see the lone pair come down and go like this. And so we could have a resonance structure like that. So there's two resonance structures for this conjugate base. But when you compare B, look at what you can have happen. Those electrons could go there, and you would get this resonance structure, like this. But then what else could you have? You could have a third resonance structure, where the lone pair here comes down, goes there, and goes like that. You see how B has 1, 2, 3 resonance structures? So when you compare B and E, you see that B has more resonance structures, and more resonance structures stabilizes that negative charge. So you're going to expect B to be lower in energy than E, like that. So if we number these based off of stability, which one's the most stable? We would say that's number one, and then C, that's 2, and D is 3, 4 is B, and E is 5. All right. And what does that mean for us in terms of which is the most acidic acid in this list? So we've ranked the stabilities of the conjugate bases. So what that means is that since this is the most stable conjugate base, that makes this guy the most acidic. Okay? Now, what's another way that we could look at that? So that's how we do it. So what's the most acidic? it follows these same numbers. This is the most acidic, 2, 4, 2, 3, and 5. So let's try to understand why is this the most acidic from an energy perspective. If you just remember this part, you'll get the rankings correct. You find the most stable conjugate base, that corresponds to the stronger acid. That's the strongest base, the lowest in energy base, conjugate base makes the stronger acid. So let's look at it from an energy perspective here. So this in blue right here is the conjugate bases and their stability. Well, what if we draw a very similar energy diagram, okay, right next to it, but instead of looking at conjugate bases, let's look at the acids. All right. Now look at this. So we'll call this A and that A. I'm just going to distinguish, this is the conjugate base, this is the acid. So the A of the conjugate base is the highest in energy acid, and so forth. D, B, and E. Okay? So if you want to look at it from this perspective, what is the stability of the acids? You'll notice that A is the highest in energy. Why? Because it has a charge, and everything else is neutral. That has a charge, so that's going to be the highest in energy. And that makes this guy the most acidic because it's the highest in energy. The A acids, like, life is hard up here. I need to react with something. And if I react with something, what happens to its conjugate base? Its conjugate base now, or the new molecule, is very stable. It's the lowest in energy. So that's why this is the most acidic, because it's so high in energy, so unstable, it wants to get rid of that second proton to look like this. In contrast, why is E, or this guy right here, okay, why is that the least acidic? Well, look where it's at. It's right here. It's the lowest in energy. So it's so low, why would this guy even think about, hey, if I give up my proton, I'm going to turn into the highest in energy species amongst these 5. That makes no energetic sense. And so that's how I like to view it. I always do the conjugate base first. That's always is the best way to go. Analyze the stability of your conjugate bases to figure out the strength of your acids. All right? As always, if you have any questions or concerns, please reach out. I'll be more than happy to help.